Welcome back to the Quantum Science Seminar. This is episode 8, and today is all going to be about quantum transport. As usual, you're welcome to ask questions during the talk. Please do so via email to quantumscienceseminar@gmail.com or use the YouTube live chat here on the right or at the bottom of the screen. Thierry also agreed to take a break in the middle of the talk where we're going to start answering some of your questions, and then there will be another question session at the end. And also, don't worry if there's more questions than can be answered during the talk. Thierry also nicely agreed to answer all these questions in written form, and we will post them on the website later. Please also note that, again, there's a time delay between what you see and what we do of about half a minute. And with that, I'd like to hand over to Andrew, who's going to introduce our speaker today.
So, hi everyone, and welcome to the seminar. It's a great pleasure today to introduce our speaker, Thierry Giamarchi. Thierry is originally from France, where he studied in Paris, and since 2002, he's been a full professor at the University of Geneva in condensed matter physics. Thierry's known for a lot of research contributions across very broad areas, but especially as one of the leading experts in the physics of low-dimensional systems, both in solid-state physics and in the last years, particularly with applications to cold atom systems. So Thierry, we're very much looking forward to your talk and hearing more about the recent developments in this really exciting area.
So thank you very much, Andrew, for the very kind introduction. And I seize the occasion also to thank Sebastian and Laetitia as co-organizers, as well as yourself, for the invitation to give a talk in this Quantum Science Seminar series. I think it's a very nice substitute in this period where we cannot have direct contact to have this series. So I will indeed tell you today about quantum transport in essentially cold atomic systems. I'll mention a little bit condensed matter as well. I want, of course, to tell to the people who are watching the video. So first, welcome, and thanks for watching this seminar. Don't hesitate if you have questions. This is not a marathon. We'll cover what we'll cover, but it's very important if you have questions that you transmit them, and we will stop at two places during the seminar to try to address the questions that you might have. This is the website of the group if you want to know more about the type of research we are doing. And of course, as usual, you will find the name of the department that I'm in, and of course, the various sponsors that helped for this research. So without further ado, let's let me jump, and hopefully the slide I should be able to change slide, which took a little bit more effort than I would have expected. So before I go to the seminar, let me show you the people who actually did the work in the talk. So this was work where we did, of course, a lot of theory, which is the job of the group. And this was done with various collaborators. Shunu Shino, who is now in Waseda University, Piotr Grysins, Anne-Maria Visuri, Sebastian Greshner, Michele Filippone, and Charles Bardin, who were at the time postdoc in my group. And we were very, very fortunate to have a fantastic collaboration with the experimental group of Tilman Esslinger and Jean-Philippe Brantu, at the time at ETHZ. Now this has branched to École Polytechnique Fédérale de Lausanne on the cold atoms, and I will mention more this collaboration a little bit later in the talk. Okay, so what this is all about. So I don't think I need to tell people about transport, because everybody has done a transport experiment one day in his or her life. It's the most routine probe to test the property of materials. Here is the simplest transport experiment that you can do, where you take a battery and then discharge it through a system, here the light, the lamp, and in a way, what you do is you use the way this transport experiment goes to test for the properties of this material here and decide whether it has interesting things. Is it a metal? Is it an insulator? Is it a superconductor? And so on and so forth. So this sounds extremely simple. And I would say in condensed matter, this has become a kind of bread and butter of many experimental groups in the world. But actually, I want to point out that if you think theoretically on how to explain the transport property of a material, this is actually a rather complicated question, because you have a system which in general is a quantum complicated system with 10 to the 23 degrees of freedom, which are all interacting together. And you're furthermore driving this system out of equilibrium by imposing a current. Indeed, you're reaching a steady state, but still the system is pushed out of equilibrium by the presence of a non-zero current which is flowing in it. And we are not very well equipped to deal with this out of equilibrium situation. We know very well how to deal with equilibrium systems. Boltzmann gave us the answer. We know we should take averages with distributions which are exponential of minus the energy of the system divided by the temperature. But here we don't really know what to do. So this is a very interesting theoretical field because we do not necessarily have the good tools to tackle this problem. Now, in a typical situation, of course, because it's so complicated, people try to evacuate the difficulty of being out of equilibrium and use tricks called linear response theory and so on and so forth, on which we will come back. So the thing I will describe in the whole talk, in the whole 40 minutes or so which are remaining, is always a situation like this. I have one reservoir of particle here, which is on the left. I have a system which is in the middle, and then I have something on the right which will collect the particles. So this can be just a voltage difference between the reservoirs on the left and the reservoir on the right. And this is the caricature, the theoretical caricature of the experiment you see on the top. And this encompasses many, many situations. For example, here is an image of a scanning tunneling microscope, which is used now routinely in many labs in condensed matter. Here it's a little bit different. The reservoirs, one of the reservoirs is the tip of the microscope. The other reservoir is the system itself. And my little white segment here is actually the vacuum, which is in between the two systems. So here the reservoirs are interesting, but in most of what I will tell later, the system, the white part here, will be the interesting part, and the reservoir will just be there, just like the battery here, to impose a current, which will go through. Very often, as I was mentioning, we only want to apply a very small voltage difference between the reservoir, and then we can cheat and use the fact that the response will be linear, so the current which will go through the system will be proportional to the voltage. This is not always the case, and actually I will show you examples where this is grossly wrong. So what are the questions we want to ask? The first one is, of course, what is the current voltage characteristics? Why? Because, as I said, it reflects the property of the material which is inside the system. If you have a metal, if you have an insulator, is this insulator due to interactions, for example? If my system is disordered, is the disorder changing the nature of the current voltage characteristics? And indeed, it does. You know very well that disorder leads to diffusion, or worse, to something called Anderson localization, which transforms quantum material into an insulator. So measuring and understanding these characteristics, current voltage, is the crucial question. Now, methods. I will say very little during this talk about methods. I'll try to show, of course, a couple of results and calculations. The methods, I would say, whatever works, what you can make work. And there are many names. And again, I don't pretend to cover all this, but if you have questions, don't hesitate to ask. So people are using linear response, which goes for transport by the name of Kubo formula. There is something called memory function. There is a very beautiful method, which is called the Landauer, or sometimes the Landauer-Büttiker methods. And there is more general techniques which deal with out of equilibrium techniques, which are called the Keldysh method. All these methods are generic methods that you can in principle apply to understand the transport. Of course, devil is in the details, and this will depend on which precise system you will look at. For small voltage, as I was saying, we can expect usually a linear response. And then because you have these two reservoirs and the system which is in between, you can expect in general that the voltage will be proportional to the current. So it's the same relation that I write in opposite direction. And this defines a quantity which we all know, which is the resistance. And usually when you connect a system to contact, you have two parts. You have the resistance of the system itself, and you have a resistance, which is the contact resistance, which is due to the very connection of the system to the contact. And this is especially important, as we will see later, when the resistance of your system is zero, because you manage to get a perfect conductor in your system. Now, at the moment, I've mentioned and showed an example of charge transports, but I want to emphasize, and I will discuss partly in the talk, other form of transport. Instead of putting a charge imbalance in the reservoirs, you can put a spin imbalance in the reservoir, and then you will measure the spin transport. You could also put a difference of temperature between the two reservoirs and wonder how charge is transported, or wonder how heat is transported from one reservoir to the rest. So all these aspects are, of course, various aspects of transport. And of course, I will not be able to address all of them during this talk, but I just want to mention that they exist, and one has, of course, very interesting theories in order to compute these quantities. Just to mention that in cold atoms, it was a little bit more difficult to realize this system, this type of measurements. And actually, the key experiment that showed that this was possible was done only recently, relatively recently, in 2012, in the group of Jean-Philippe Brantu and Tilman Esslinger in Zurich. And what they realized was essentially a system in which they were having a big blob of atoms that they were constraining with a laser into a big blob on the left, a big blob on the right. So here is a more realistic view. This is an image where you see the big blob on the left, the big blob on the right, which constitute the two reservoirs, the reservoir on the left, the reservoir on the right, as I was showing. And you can manage to imbalance the population between these two reservoirs. And then the little structure which is in between these two objects is the system you want to study. And then you can discharge, let the atoms, okay, from left to right or right to left, go through the system. And this is the perfect realization of the battery discharging into the resistance that I was showing here. And actually, when you do the measurement, so here is the measurement of the number of atoms in the left reservoir as a function of time. And you see the exponential decay, which is characteristics of an RC circuit. And when you extract from this time dependence the current voltage, the voltage is proportional to the population imbalance in the reservoirs, you find essentially a nice linear relation. So you rediscover essentially Ohm's law, the fact that the current is proportional to the voltage with a certain constant, which again is the conductance of the system. But of course, using this device, you can do things which are much more sophisticated, because now you have all the control of cold atoms at your disposal. So in particular, you can make the reservoirs interacting, or you can make the system interacting, or you can put stuff inside the system. And we will see several examples of this situation. So let me show you very briefly one example, and then we'll make a break. So if you have questions on these generalities, you can ask them. Here was something that was studied a lot in condensed matter, and the theory of this was made already some time ago, essentially in the mid-90s. This is the question on what happens when you take two superconducting materials. Here is a left reservoir, which is a superconductor, a right reservoir, which is a superconductor. These are films which are deposited on the plastic membrane. And the reason you do the plastic membrane is that you can push here below with a rod, which cracks the connection between the two. So you get two reservoirs which are separated by vacuum. And this is called a quantum point contact, because you get one superconductor, and tunneling of particles through the vacuum between these two superconductors. Let me show you the current voltage characteristics for various size of the cracks, if I could say here. This is the voltage normalized to the superconducting gap. This is the current, okay, normalized also. And you see very non-linear. So this is proving that you cannot always use linear response. This is very non-linear current voltage characteristics that depend extremely strongly about the tunneling amplitude that you get between your two superconductors. So understanding these properties allows you to understand the properties of both the superconductors, and also, of course, on how particles can tunnel from one superconductor to another superconductor. Now, in this device, it's very difficult to get good junctions. It's easy to get junctions where the tunneling is extremely weak between the superconductors, but not so easy to get junctions where the tunneling is very good. Actually, this is much more easy to do in a cold atom experiment. So this is exactly the experiment I showed you before, but this time you make an attraction between the two reservoirs here. So these reservoirs contain fermions with two spin species, just like in a normal metal, and you put a contact interaction that attract the spin up and the spin down, and these two reservoirs turn into normal S-wave superconductors. And then here you realize the quantum point contact, where the Cooper pair will tunnel from one side of the system to the other. And we helped a little bit with the theory. In particular, Shun Ushino was doing this analysis together with Dominic Hussmann in the group of Tillman-Esslinger. And here are the theoretical curves, the red curves, together with the experimental data, which was taken in the group of Tillman. I won't go into the detail because I want to deal with much more recent work in which the system was not just vacuum, but just to say this was already a highly non-trivial mechanism that was unraveled by this experiment, because the tunneling actually reveals something called as multiple Andreev reflections, which is that if you want to have a particle which tunnels from one side to the next, it should be accompanied by the tunneling of many Cooper pairs together. Otherwise, the tunneling cannot take place because of the gap that exists in the superconductor. So this is a very fancy mechanism that people were trying to understand and analyze. And analysis of the transport in this material, where you can control extremely well the strength of the interaction. There are essentially no adjustable parameter here, because we are dealing with cold atom experiments, allowed to really understand this multiple Andreev reflection mechanism. So I think it's a good point to stop before we go to study what happens if we have a one-dimensional wire between the two reservoirs, and take questions on what I would call the generality of transport.
So we have a question from Bill Phillips that asks, there are various senses in which systems can be 1D or point contacts. Could you say a bit about these for atoms and for condensed matter?
Yes. So first, thanks for the question, Bill. Great to have you. As usual, a great question. So 1D. So first, 1D means that the quantization in the transverse direction, the size of the system is small enough that due to quantization, the separation in energy level is large enough compared to temperature and or interactions, so we can completely forget all quantum numbers corresponding to the transverse direction. So only quantum numbers corresponding to the longitudinal motion will be important. If the wire is long enough, we can forget in first approximation quantization in the longitudinal direction, and then we have a 1D wire. If the wire is short enough, then by the same essentially reasoning, you go to a zero-dimensional wire if you want, and then that is essentially the quantum point contact. For superconductors, one has to be a little bit more careful because there is a proximity effect that makes that the superconductivity of the bulk extend by a size which is psi 0, the coherence length, which in a superfluid, I guess, would be called the healing length, inside the channel. So I would say as long as the channel is not too long compared to this Cooper pair size, we can consider that we have a 0-dimensional structure. So I hope it answers the question.
So this was the main question up to now. So maybe let's go on, Thierry.
Okay, so now let's consider something which is a little bit more sophisticated, which is to put between the two reservoirs, not just vacuum, but to put really a 1D wire and ask ourselves, okay, what can we expect in these situations? So first, let me mention a very beautiful verification that was done by the same group in 2015 of something which people had done in condensed matter before, which is what happens if your reservoirs are non-interacting. You have a 1D wire between the reservoirs, and you try to measure the conductance. So the voltage difference is not too large. So the current will be proportional to the voltage. And let's say the voltage difference is not too large. And you try to see what is the conductance, so the ratio between the current and the voltage in the channel. And there, something remarkable, which was predicted by Rolf Landauer, essentially happens, is that you find that there is conductance quantization. And the reason why you get this conductance quantization is because the 1D wire is a perfect transmitter. Its resistance is actually 0. So everything is dominated by the contact resistance between the reservoirs and the system. And this contact resistance is completely independent of the length of the system and so on. And it's easy to check, well, actually not so easy, but not too complicated to check that because you get this perfect transmission, the conductance should take the magic value 1/h, essentially, and per channel of transmission. And this is something that you very clearly see on these curves here, where you get the gate potential, which will control how many transverse channels will exist in this 1D wire. So the 1D wire can transmit 1 transverse mode or 2 transverse mode or 3 transverse mode and so on. And you see that if you get nothing in the wire, the conductance is 0. And then you change the gate potential and you put the first transverse mode in the wire. So you get 1 channel of transmission, the conductance go to 1 in unit of 1/h. Then you put 2 channels of transmission, it goes to 2 and so on and so forth. And this is a beautiful verification of this quantization of conductance, which of course only exists if you get non-interacting particles, both in the reservoirs and in the wire. The reason why it's not nice steps here is because unfortunately the experiment is done at finite temperature, and this is of course spoiling a little bit the quantization. Now, one question is what happened when you have interactions? If instead of being a non-interacting channel, what would happen if your channel is interacting? And there we have to realize that 1 dimension is really special. And the reason is because in higher dimension, when you get interactions between particles, the particles got dressed by this interaction, but they retain their nature of individual particle. For fermions, it's called Landau Fermi liquid theory. So essentially, interacting particle kind of remain a little bit like free particles, and they scatter and they transport like little balls which are hitting each other and so on and so forth. In 1 dimension, it's completely wrong. If you put particle which interact on the line, this particle will push the next one, which will push the next one, which will push the next one, and so on. So everything is transformed into collective motion. So the notion of an individual excitation does not exist. Now you would say, what is the consequence for transport? Well, it's profound. Let me show you an example. If you want to know more, I can only, of course, recommend you a good book on the subject, but you have other reference which have been put on the webpage of of the talk. But one particular example of this is the concept of spin charge separation. Let me look at the one-dimensional systems where I would have particles here, which would contain a charge and a spin, like an electron, for example. If I am thinking in terms of free particles, when a particle moves, it transports its charge and its spin. And there is nothing you can do to avoid this. So roughly speaking, the transport of charge would be very close to the transport of spin. It's not the case in 1D. If I remove a particle, I've removed the charge, but I've also removed the spin up here. But now let this excitation propagate, for example, by spin flipping the other particles. And you see that after a while in a part of the system, there is something where no charge is missing, but I get two spin down which are close to each other. So one spin up is missing. So this excitation has a charge, but doesn't have does a spin, sorry, but doesn't have a charge. It's called a spin-on, and it's a collective excitation which will not participate to charge transport. On the other hand, here you see that I have now something that can move and that can transport the charge which is missing, but in a way which doesn't distort this kind of caricatural antiferromagnetic arrangement that you see here. This excitation is called a holon, and it carries a charge but no spin. And both are actually topological excitations. So the topology in 1D is the norm rather than the exception. And you immediately see by this little example that you can expect practically a very strong difference between charge and spin transport. But actually, one thing which is less obvious to see is that the charge transport itself will be very drastically affected because of the collective nature of the excitation. So to see this, let's look at what would happen if I take a 1D structure and I put a very weak periodic potential on the top of it. If I have no interaction, you all know the answer. If I put a small periodic potential, I get a band insulator. And then it depends on the filling of the system. But if I have 2 particles per minima of the periodic potential, I will open a small gap and I will have a field band, and then I will have an empty band on the top of it, and so on and so forth. So this is very simple. On the other hand, if I put interactions among the particles, in particular attraction among the particle, I will form a superconductor. And we know that superconductors are resistant to disorder, to potential. So naively, a superconductor should be resistant to a very weak periodic potential. So there shouldn't be the gap of the band insulator if I have a strong attraction. So we could expect naively to have a competition between the formation of a band insulator, if the interaction is 0, to superconductivity, which will completely ignore the weak periodic potential if the attraction is very strong. And actually, in higher dimension, this is something that exists. And here is a very beautiful paper by Philippe Nozière, where they study this, and they find indeed a phase transition as a function of the strength of the superconducting gap to the band gap between an insulating phase and a superconducting phase. Now, this is sort of what we would expect naively. So is it true? And in particular, is it true if we have 1D? The problem is that if you want to test experimentally this in condensed matter, it's practically impossible because you don't have reservoirs where you can put a local attraction. Electrons repel, essentially. And it's very difficult to do a channel, a 1D channel, on which you can put a very weak periodic potential on the top of it. But fortunately, you can test with atoms, with cold atoms. So let's take again the same experimental device, but this time using light, you could impose a periodic potential, and this was done by Martin Lebras, in particular, again, in the group of Tillman and Slinger, and Piotr Grissins was doing the theory of this particular experiment. So here is the reservoirs that you see only the edge here, and then you get the 1D structure on which a periodic potential has been imposed. It's not as long as perfect as one would like, but it's as good as one can reasonably reach. no interaction, we do expect a band insulator. And because it's non-interacting, we can use this one of these methods that I was mentioning, which is called the Landauer formula, which relates the conductance to the transmission through the potential to check indeed that we get this insulator. So here is the theoretical plot of the conductance versus the gate potential. This is for no periodic potential in the wire. You see at finite temperature, you see the quantization of the conductance. And you see that now if you put the periodic potential, let's take only this curve, which corresponds to the longest periodic potential available. You see that it first goes up, but then it would like to go down at a particular voltage for which there would be 2 particles per minimum of the potential, which would correspond to the field band. The reason it doesn't go to 0 is because, of course, of the finite temperature of the experiment. But clearly, there, at that filling, you should have a band insulator. And lo and behold, if you look at the experiment, again, this is the deep blue point. You see that they go up and they go down and they go up again in perfect agreement with the theoretical curve, which is what we would expect. No big surprise, this is the band insulator. Now, what will happen if now I put attraction in the channel? If I have my channel, which is itself a very good superconductor, I would expect naively that this band insulator should disappear and I should find an excellent conductance inside the system. And there, it doesn't work that way. So since my time is running up, I won't go into the detail of the calculation, but there are good machineries to deal with interacting 1D system. One of these machineries is called bosonization, which I don't want to detail. So we write the Hamiltonian of a 1D gas with interaction, with attraction. We add the periodic lattice potential. We use this bosonization formula, and we fall on something that was predicted by 2 gentlemen in the mid-70s, Alan Luther and the late Vic Emery, which is called quite justifiably the Luther-Emery liquid. And this is a very weird liquid in which there is a gap in the spin sector, so a little bit reminiscent of a standard superconductor. But the charge sector is a little bit weird because it's described by something called a Sine-Gordon, by something called a Luttinger liquid. So I don't want to go into the detail of what it is, but suffice to say that this Luther-Emery liquid pins on an arbitrarily small periodic potential. So if this liquid is formed, you can check that it will completely lock on whatever strength of periodic potential you put in the system. So the intuition, and again, let me pass all this. So the intuition, which was that if you had non-interacting, okay, if the filling is not 2 particles per side, you get a metal. And if the filling is 2 particles per side, you get a band insulator. Actually, in 1D, when you put attraction, remains practically the same. Your Cooper pair could be much larger than the minima of the potential. It doesn't matter. This is just a cartoon here. But you could say that the Cooper pair sort of get localized in the minima of the periodic potential, and schlock, they stay insulating. So you get the very strange fact that you can crank up the attraction as much as you want in the 1D system, and it stays an insulator even in a tiny, weak periodic potential. So there is no superconductor band insulator transition, regardless of the strength of the interaction. And lo and behold, here is the experimental data. So this is the theoretical prediction, which was fun to work out. Here are the theory curve, which have been shifted for the conductance for clarity. And you see here that the minima sort of stay the same. These various colors correspond to various interaction strength inside the channel. And lo and behold, when the experiment is done, you see that essentially you keep your insulator, which now is not a band insulator anymore, but this is a pinned Luther-Emery liquid. So this shows the various peculiarities that you can get of a system when you have these very unusual aspects of collective excitations that you can get in a one-dimensional system. It gets even weirder if now you look, instead of looking at the charge transport, you try to look at the spin transport. And this was done mostly by Anne-Maria Visuri with a postdoc in my group. And this was done again in collaboration with Martin Lebras, Sebastian Hausler, and Laura Corman in Tillman Esslinger's group. So this is the same question than looking at the charge transport, but this time let's do spin. Let's say instead of measuring the total current, let's measure the spin current, J up minus J down. And instead of putting a charge imbalance in the reservoir, I just keep the same charge in the two reservoirs, but I put one reservoir with spin up and one reservoir with spin down. And so you can define like this spin transport, and you immediately feel that you know the answer. Because if there is a gap in the system, spin up and spin down attract. If now you try to move in opposite direction, the spin up and the spin down, it will not work. So if you have a superconductor, you would expect the spin transport to be zero, to be very small. On the other hand, if the particles don't interact or are repulsive, you can have the two spin current move in opposite direction, and you should have a strong spin transport. This is the type of device that we are looking at again. And actually, you can define much more generally the whole matrix of spin up current, spin down current as a function of the chemical potential of spin up and spin down. And it not only allows you to define the spin conductance, which is the one which I define on the top here, but you can define a fun quantity, which is the spin drag. Let's imagine you put only a voltage for the spin up. Very naturally, you will have a current of spin up. Another question you can ask is, do I also get a current of spin down? Now, if you have a gap, you would say, oh yes, because every time I will move a spin up, it will drag a spin down with it. So by just imposing a voltage difference for the spin up, I should be able to generate a current of spin down. On the other hand, if the particles don't interact, you will get no spin drag. The spin up will move and the spin down will stay motionless. And all this is connected to these two transport coefficients here that you can compute. And actually, it's connected to the charge conductance and the spin conductance. So I just mentioned the spin drag because this is something that is quite, I would say, counterintuitive. And there is something in condensed matter which is called the Coulomb drag, which is a little bit the same philosophy, where you say, if I pass a current in one wire, can I drag a current by Coulomb interaction in a second wire which is nearby? So here it's a little bit the same thing, but with the two spin degrees of freedom. Okay, so what is the situation? So again, I won't go into the methodology. You map using this bosonization to an Hamiltonian, which is called the Sine-Gordon Hamiltonian. You use various techniques which are summarized here, which I don't want to discuss, memory function, renormalization group, and so on and so forth, but don't hesitate to ask questions. And let me just show you the results. And let's focus on the curve B here, because that's, I think, the most interesting curve. There are two scales. One is the size of the wire. The other is the size of the Cooper pair. And let me assume this is the case for curve B, that the size of the Cooper pair is much smaller than the size of the wire. Then I have a third scale, which is the thermal length, which is inversely proportional to the temperature of the system. And now let me reduce this temperature and look at the spin conductance. What you see first is that the spin conductance goes smaller. And that's exactly what you would expect. I form Cooper pairs. This Cooper pair completely lock a spin up and a spin down. So I cannot have two spin currents moving in opposite direction. My spin conductance is zero. But again, something weird is happening, because when your temperature length reaches the size of the wire, the conductance goes up again and goes back to perfect conduction. Of course, this would assume that you can go to extremely low temperature, that your reservoirs are large enough, and so on and so forth. But you see that you get this very counterintuitive result, that it doesn't matter that whether you have a gap in the 1D structure. Because of quantum effect, the system becomes again, and quite counterintuitively, a perfect conductor again. So this is something we would love to test in cold atoms. Unfortunately, the existing experiments are here for the moment. They cannot go down enough in temperature to really test the fun part, but at least we can see whether we do a good job on this part. And lo and behold, I would say we do. Here is the calculation of the conductance as a function of the density in the channel, and using a method which is the so-called memory function method. And when we compare with the experiments that were done in the group of Tillman, I won't say we find a fantastic agreement, but at least we seem to be in the right ballpark for the variation of the conductance as a function of the scattering length of the system. So this spin transport is a less usual quantum transport, and it shows again the very unusual aspects that you can get in a 1D structure which is connected to reservoir. So I think it's a good time to make a little break and take questions on these two parts. And then if time permits, I will say just a very short word on the last part of transport, which is the Hall effect, which is what happens if you have now a magnetic field which is added to the system.
So we have again a question from Bill Phillips, who says, this talk has been about fermions. What about bosons? We don't have a Fermi energy or pairing, but we do have superfluidity and features like transverse excitation, quantization in a channel.
Yes.
So what kind of things are the same and what are different?
So that's excellent questions. And now it's a very difficult question to answer. So let me go back first to this one. There I have fermions, it's true, but the Cooper pair is a little bit like a boson. So what I'm describing here for the spin Luther-Emery liquid is actually extremely similar to the Mott transition of bosons in a 1D potential. So with bosons, one can also redo part of this analysis. The thing which makes it much more difficult with bosons is that I can compute the conductance of the 1D structure, but treating properly the reservoirs is a much more complicated business, because now I certainly cannot take non-interacting reservoirs. If I want to have something which is reasonable, I need to properly treat the interactions in the reservoirs. So many of these things for 1D, if you have bosons with repulsion, is very much similar to fermions with attraction. And you can think mentally of the Cooper pair as a kind of hardcore boson, which will have a nearest neighbor repulsion. And then you can make the connection between the two. The bosonization technique that I didn't discuss actually allows to treat as well repulsive bosons and repulsive or attractive fermions. So one can also do similar studies in the case of bosons. There are, I did some of them, so I'll be happy to answer in writing if to give a more precise answer. But to put bosonic reservoirs is actually paradoxically a little bit more complicated, unless you do the approximation that just the phase of the reservoir is important, in which case this is a very, very simple thing, because you just impose the phase of the system at the end.
So thanks very much, Thierry. We have actually still several other questions. So one is from Karen Hallberg. What about charge transport with repulsive interactions?
Okay, so here the reason I discussed mostly attractive interactions is because the experiment can mostly realize attractive interactions. Repulsive interactions causes a certain number of problems, metastability, and so on and so forth. Most of the methods I described are perfectly adapted and can be used for repulsive interactions as well. And actually, in the paper I was mentioning on the spin transport, we deal also with the repulsive side as well.
Okay, so there are still more questions. So Ekaterina Plotnikova wonders what would happen if the weak periodic potential that you described is tilted.
Well, in a way, the potential is tilted because there is a voltage difference at the edge of the system. So the fact that you connect the system to reservoirs and impose a voltage difference is a little bit the same than saying the system is isolated and then I tilt the potential. The difference is that the reservoirs are infinite, so the particle don't go crashing to the walls. If you tilt the system and it's in a parabolic confinement or it's in a box, you cannot reach a steady state for the current because rapidly the system will crash to the end and then this will stop the flow of current. Actually, it's all a question of time scale. I will show for the Hall effect the Giamarchi calculations, which have been done in a box by tilting the potential. And you just need to do the thing fast enough that this edge effect is not a problem. So I would say it's essentially very close to tilting the potential, pending the fact that some of the long time effects will of course be different because of the finite size of the system.
So we have as well a question from Vincent Liu, who shows interest for this many body insulator pinned laser emery liquid that is very interesting. And he asked whether this can be thought as due to the size of a Cooper pair in 1D and condensed being shorter than that of a weak BCS superconductor in 3D.
So not really. The size of the Cooper pair doesn't really matter in this calculation. Here, for the caricature on the drawing, the size of the Cooper pair seems to be smaller than the size of the periodic potential, but it doesn't matter. You could have the Cooper pair 10 kilometers, the two components of the Cooper pair 10 kilometers away, and it would still give the pinning. So this is really because there is the spin charge separation. The spin gets whatever it does, it forms Cooper pairs, get gapped, and then the charge, which is like bosons, will form a Mott insulator in this periodic potential. The real reason why you form this thing is because in 1D, even an extremely weak periodic potential is able to give you a Mott insulator. Susceptibilities can be, in general, diverge in 1D. So even a very small perturbation can lead to a very strong response. In 3D, a weak periodic potential would not be able to give a Mott insulator for bosons, and therefore the Cooper pair can move unless you go to a very deep lattice. So this is not related to the size of the Cooper pair. And if you put a very large U in 1D, very large negative U, you can get Cooper pair whose size will be one site if you are on the lattice. I mean, you can make the size of the Cooper pair as small as you want.
Okay, so one very last question, and then we should go on. So François Damanet is asking, regarding the spin transport work, in order to reach the interesting regime experimentally, would it not be easier to reduce the size of the channel instead of reducing the temperature?
Yes, that's a very good point, except for several things. The density is already pretty small. So if you reduce the size of the channel, first, you don't have many particle in the channel. And then using field theory, which assumes a finite density and whatever, becomes questionable. So yes, one has to find the sweet spot in small size, but not too small size for the channel, because you don't want the channel to be also smaller than the size of the Cooper pair. So there is a sweet spot, which probably is a good regime, but if you reduce too much the channel, first you will run into problems between the size of the Cooper pair and the size of the system, which actually correspond to curve A, where these two quantities are inverted, and then you see the minimum does not exist. And you will also run into problem because you will get 0.01 particle in your channel, which is also not super good in terms of looking at Luttinger liquids, I would say. So yes, there is probably some, I would say experimental exploratory work to find if there is a good regime in in which one could both see a drop and then going up and still be in a reasonable range of accessible temperatures and so on.
Okay, although we have still quite some questions, I think we should move on for the sake of time, and then we will come back to them at the end.
Okay, so thanks first to all for all the questions. It's really exciting. And let me just mention, I will go very fast on the last part because I think it's more to give you a flavor than really go into even the details of the results that we obtain, and move to something which is again a powerhouse in the condensed matter, which is the Hall effect, which is what happens if you pass a current in a system or put a voltage at the edge of a system, but have a magnetic field which is put perpendicularly to the system. And then you all know, you all suffered through your elementary courses on the fact that the Lorentz force is deviating the particles. They go accumulating here. They produce a counter voltage, which then make the current line straight. And then you detect a Hall voltage, which is the consequence of the current you pass into the system. And if you deal with a classical system or a non-interacting system, you get this fantastic formula, which actually is practically never correct, which is that the Hall resistance, which is the Hall voltage divided by the longitudinal current and the magnetic field, is proportional to 1 over the density of carrier. And that has, of course, be an incredibly useful technique for the experimentalists to determine the density of carriers in materials they didn't know, like semiconductors and so on. The reason I'm saying this formula is almost never correct is actually what should be computed is the curvature of the Fermi surface. And there are much more beautiful formulas. One of them, which is extremely and quite rightfully celebrated, is the Thouless-Komoto formula, which relates these quantities to topological invariance on the Fermi surface. But all this is for non-interacting particles. So we know very well, and we understand now very well, what the Hall effect measures for non-interacting particles. And as soon as we put interaction, it's a Pandora box, because it's incredibly complicated to practically compute this quantity. It's a nightmare to compute the Hall effect. But on the other end, it's an incredibly useful measurement that you can do. Just to show you the panic in condensed matter, we did a couple of years ago with Gladys Leon, who was a PhD student in my group, and Christophe Berthaud, who is a permanent member in the group. We did some calculation in perturbation on high temperature calculation of the Hall effect. And it's a nightmare. The calculation is a nightmare. Now you can say, why don't you measure it and test it? Here are the results of 2 different groups in condensed matter, a very famous group, very, very talented experimentalists, one in Paris, one is in Lausanne, on the same sample, the same system, and one finds a strong temperature dependence of the Hall effect, the other finds a Hall effect, which is essentially temperature independent. And this was 20 years ago, and the situation is still the same. So we cannot even say experimentally we think that this is right or this is wrong or whatever, because experimentalists do not agree on what is the experimentally correct result. So we cannot even compare our theories with experiments. So again, we turn to cold atoms. And first, it's fantastic because you control everything in cold atoms, but there is a major difference. They are extremely clean and relatively small. So contrarily to condensed matter, where the particles are subjected to diffusion and very often local equilibrium, here we have to study the Hall effect in a ballistic situation. So actually it's a new study. It's a range of looking at the Hall effect where no theorist had invested brain power before, because for condensed matter, it's totally different. And that's super exciting. So this is what we try to do in connection with experiments. For example, these are experiments in Falani's group in Florence, where they realized this synthetic dimension system where by using of an internal degree of freedom, they can fake having 3 different chains of particles and making particle tunnel from one chain to the other, picking up a phase, which is like putting a magnetic field. And then if you measure the imbalance between this chain and this chain, you can measure the Hall effect. And similar experiments were done in Maryland in Jan Spielman's group. And this is something which in cold atom is now, I won't say routine, but is something which is well established, well measured, and begging for theories to be made. So we've tried to play a little bit with this in view of the time, and because I would like to take questions, something we did with Sebastian Grechner and Michele Filippone, and it's very difficult. Analytic theories are very hard, so essentially we resort to essentially DMRG calculations, also of course some analytical calculations, but DMRG calculation, just to flash one of them. Let me skip this. Here is a DMRG calculation where indeed the system is brutally tilted to induce a current, and then one measures both the current and the tension which is generated on the transverse direction. And what is remarkable is that although you see that this is really not reaching any stationary state, you see very rapidly that the whole resistance is rapidly reaching a stationary state before everything crashes at the end of the system. So actually, we were blessed by a goodwill of this particular measurement, which is that even by doing a transient calculation, we can reach states which are actually long enough to have a good value, and we compare with analytic calculations when we can compare, and we can therefore compute the Hall effect, even if we have interactions in the system, because of course the DMRG doesn't care. So I don't think I have the time to discuss really the results. I refer you to the publications. The Hall effect depends on the interaction in a highly non-trivial ways, but we could find some invariant that we understand. And there are also some very interesting property of the Hall effect that I won't have time to discuss, which was due essentially to Charles Bardeen, together again with Michele Filippone and Sebastian Grechner, which is actually in this ballistic system, the Hall effect depends on how you measure it. It's not the same to attach the system to two reservoirs and measure the Hall effect, or to put the system on a ring and pass a current by threading a flux inside the system. Usually, we always assume that these two things are the same, and it's just a matter of convenience which one you choose, not for the Hall effect in a ballistic system. You see the blue and the red curve, which correspond to these two geometries, and they are different. The difference is not big, but they are different. And one of the curves shows very clear plateaus, which I won't discuss here, but which are connected to a topological invariant in the system. Okay, that's all what I will say here for the Hall effect. We are checking whether these results which we obtained for non-interacting particle are robust to interactions. And then again, we have to go to the numerics. But this is very exciting times, I would say, because we are now in a good position to compute and hopefully measure at the same time these properties. So I think it's time for me to conclude. I presented you various calculations and measurement of quantum transport. I think quantum transport is a very exciting field. It's a difficult field because, again, it's intrinsically something which is out of equilibrium. Cold atoms have proven to be fantastic system to tease the brain of the theorists for this aspects. There are novel situations, there are novel effects. One can test things that were in the air on the theory side, but we could never test on the condensed matter side. Luther Emery liquid, spin transport, and of course the Hall effect. And as I was mentioning, there are, I think, many exciting possibilities and challenging theory questions on which we have to sweat, but this is very exciting to do. So on that, I thank you all for your attention, and I think I will wrap up and take any additional question that there might be.
So thank you very much, Thierry, for the great talk. Of course, it's so interesting that there are still many questions that come up. So there is another one from Bill Phillips that wanted to follow up on the question about the tilted potential versus the two reservoirs, and would like to know when you would get Bloch oscillations instead of conduction.
That's a very good question. So with the reservoirs, actually, we will probably never get Bloch oscillation. And there, I'm not sure I'm not saying something stupid, so I should check myself. But of course, with a tilted potential, you will get Bloch oscillation in a ballistic system when your acceleration will be such that you reach the zone boundary in the system. With the reservoirs, now that I'm thinking of it, I think technically one could also get Bloch oscillations, but the reservoirs provide a form of dissipation. So that's a good question. I think the honest answer is I don't know. Of course, with a tilted potential, you will get the Bloch oscillation. It's a non-dissipative system and so on and so forth. With the reservoirs, that's actually a very good question. I don't know.
So there is a related question by email from Jakov Yudkin that would like to know to which extent this transport setup is the same or different as a macroscopic double well potential, because he thinks it looks very much like a macroscopic double well potential between the two reservoirs, and whether you could see, for example, rabbit flopping between the two reservoirs or so.
So again, I think it depends a little bit how long and how complicated is the system which is in between the two reservoirs. If you have an extremely short system like one site, or then of course what you see is mostly conditioned by what you put in the reservoirs, to some extent of course also by whatever is your site, but especially if you don't put anything between the reservoirs, then this is indeed like a double well, very much like a double well. If you have a very long system in between and the system is interacting or contains impurity and so on, the resistance of the system will be completely dominated by the central part. And actually, let's be naive. Let's forget about localization aspects or whatever. The resistance of a 1D wire is proportional to the length. So even if the system is a good conductor, if it's long enough, the resistance of the system will always dominate the contact resistance. And you can ignore the contact resistance, which means in first approximation, you can ignore the reservoirs. And that's why formulas like the Kubo formula, which is just saying, let me measure the current correlation inside the system, and I have no reservoirs, I have no nothing, were also very successful to describe realistic experiments where you do get contacts and pass a current inside the system. It's because you lose the coherence, you lose the possibility to sort of get a coherent oscillation across the whole system. So I think that's a very, very good question. And I would say for the Hall effect, it's crucial. For example, how do I go from my ballistic Hall effect to the one I was saying I establish a local equilibrium here because of impurities, because of temperature, and then I can again do a calculation without reservoirs using the Kubo formula. So how does one go from the double well to what I would call Landauer-Büttiker, two reservoirs and a system in between, how this crossover takes place? I think that's one of the interesting and difficult question to answer in the field.
So we will take a very last question. Then Thierry nicely agreed to answer all the other questions that are still left. There are many interesting questions in a written form, and they will be posted in the website. So the last question we take is from Gal Ness, that would like to know whether it would be possible to periodically flip the direction of the chemical potential imbalance in order to study some AC voltage characteristics.
That would be fantastic. I think the question should be asked to the experimentalist. So maybe I can redirect the question to Bill Phillips. Yes, of course. Doing the AC current would be very nice. You have to do it fast enough or slow enough measure, but that would be nice. Another possibility, and perhaps simpler possibility, is actually, if you have an optical lattice, is to shake horizontally the optical lattice. And that's a calculation we did with Akiyuki Tokuno a couple of years ago. This is exactly like applying an AC electric field on the system. So both methods are in principle possible. Probably the shaking of the optical lattice is a little bit simpler than oscillating the population in the reservoirs. The way they do it is that they prepare the reservoirs with an imbalance and then they discharge the capacity. So I doubt that they can really do this oscillation, but again, I think the simplest is probably either to play with fluxes, and then I don't see no reason why you could not oscillate the flux, or as I said, take an optical lattice and shake it horizontally.
Okay, so I think we really have to stop here for the sake of time. But again, I mean, don't hesitate to send the questions by email because they will be answered. Thanks again, Thierry, for proposing that. And thanks very much in the name of all of us for the really nice talk. Yeah?
Thank you very much for the invitation. And thank to all the people who watched and asked questions. So thank you very much.
Yeah, thank you very much, Thierry, also for a really wonderful talk. And thanks to all of you for asking so many questions. Next week, I just would like to announce we will have Junier, who will speak about creating a Fermi gas of polar molecules. And if you want to get notified of what's going on, please go to our website, quantumscienceseminar.com, subscribe to our email list and to our Google Calendar. You'll get all the updates every week. Also, please check out our sister seminar, the AMO seminar, where tomorrow they will have Jakob Reichel talking about spin squeezing. And in fact, next week, I think they'll have Tilman Esslinger, who will probably talk about some of the experiments that Thierry just talked about. With that, I'd like to thank you for your interest, and we hope to see you again next week. Same time, same place. Bye.